We are going to start a new topic today, that is on order to disorder transformations. But before I start, because this is a new subject which may not have been introduced to you previously by any of the subjects, we have to give some examples. Let us take example of copper and gold phase diagram. Copper and gold phase diagram is a very classic phase diagram in the sense that at high temperature it shows a complete solid solubility, liquid solubility and solid solubility both, with a isomorphous type of phase diagram. As you can see over here, liquid goes to alpha, and this is very typical of this copper gold, copper silver phase diagrams. But what happens at lower temperature is very interesting. At lower temperature, depending on the compositions of the alloy, that is depending on the concentrations of the gold in the alloy, three different types of phases can form. One which is a stoichiometric composition of copper 3 Au, second one stoichiometric composition of copper 50, gold 50, that is copper AuCu, and third one which is a stoichiometric compositions of CuAu3. And these three phases are intermetallics because they are compounds, but they have a solid solubility range, like Cu3Au can form from about 20 atom percent of gold to about 35 atom percent of the gold. But you know what is interesting for our discussion is that in Cu3Au the atoms do not occupy any positions in the lattice. Remember, alpha is basically FCC phase, FCC solid solution between copper and gold. So, in FCC solid solutions, if it is a random solid solutions, the positions of the cube corners as well as the faces of the cube will be occupied by both gold and copper atoms. There will be no distinctions of side specificity of gold and copper atoms in these positions. But the moment Cu3Au forms, and at temperature below 390 degrees Celsius temperatures, copper atom preferentially sits on the face center positions of the unit cell and gold atom sits on the cube corners. So, that means there is a proper segregation of the atoms in the unit cell itself. So, that is what is known as disorder to order transformations. There is high temperature, alpha phase was a disorder phase in which there is no side specificity of the atoms in the FCC unit cell, but at lower temperature, that is below about 390 degrees Celsius temperature, this specificity does develop, and because of that copper and gold atom goes to the specific lattice positions in the unit cell. This happens mainly because of the energetics of the systems, which we will discuss later. So, that is the main reason or main definition of disorder to order transformations. Same thing happened for the gold copper alloy, that is AuCu. Here actually the FCC solid solutions which was present at high temperature, what is known as alpha phase, at about 410 and below, these copper and gold atoms actually goes into the specific sites. Like copper atoms only occupy in FCC unit cells the 4 face center positions on the FCC unit cells, and gold atom occupies the corners as well as 2 face center positions. That is how it has become 50-50 alloy compositions. CuAu3 again is another analog which can be thought of like a Cu3Au. What actually happens is that in case of CuAu3, gold atom goes to the face center positions and copper atom goes to the corner positions. So, in all these three examples which I have just now talked about it, the atomic positions are specific for a particular type of atoms, and that is what makes them order structure. Okay, let us give examples of that. Just now I told you the examples of the alpha to AuC3 structures, Cu3Au structure rather. So, in a disordered solid solutions which is at high temperature alpha phase, this is alpha phase, As you see here, there is no specific positions where specific atoms can go. It is an average situations, like the cube corner or face center positions can be occupied by either copper or a gold atoms. There is no specific way of demarcating that. But on the other hand, when below 390 degrees Celsius temperature, this situation is completely changes to the one which is shown on the right side. As you see here, the copper atom goes to the face center positions, 6 face center positions are occupied by the copper atoms, and the 8 corner positions are occupied by the gold atoms. And as you know, in FCC unit cell, the corner atoms are shared by with 8 other unit cells, therefore 8 gold atoms actually contribute to 1 atoms to the unit cell, and 6 copper atom contributes to 3 unit atoms to the unit cell. That is why actually you get Cu3Au compositions, and this structure is known as L12 structure, because this structure is not same as a FCC structure. So, we have to have a different notation to demarcate that. So, that is actually disorder to order structure. Disorder structure was this and order structure was the right hand side. Similar thing can happen in AU-CU structure, that is what is shown here. So, below about 485 actually, let me check once more, 410 actually, below about 410 degrees Celsius temperature, this disorder structure will transform to order structure. What actually happens? Changes in a disorder structures, any atomic positions is an average occupancy. That means whether it is a corner or it is a face center, we cannot specify that the particular atom, whether gold or copper, is occupying their positions. It is basically an average kind of situations where each atom can take different positions, but finally it is an average specific positions cannot be talked about it. On the other hand, if it is below 410 degrees Celsius temperature, then copper atom preferentially goes to the middle layer. As you see here, basically copper atom occupy 4 face center cubic positions and gold atom occupy 8 corners plus 2 face center cubic positions, which are like that. So, that means it basically start developing a layer kind of arrangements of the atoms. Okay, first layer is basically occupied by gold, second layer is copper, third layer is second gold, fourth layer is copper, just like the sequence I told you it develops. And these kind of things are known as L10 structure. Remember, L12 is order face center cubic structure, L10 is also order face center cubic structure, but this is not a cubic anymore, this is a tetragonal unit cell. Because of the atomic size difference of the gold copper, the C axis actually increases a bit, that is why it becomes a tetragonal structure. Remember, these notation L10, L12 or other notations which you will talk about it, they are specific for the order structures. Order means atomic positions are specific to a particular atom. You have to talk about occupancy of based on a particular type of atom. You cannot talk about average in case of order structure. So, these are all FCC alloys which has undergone disorder to order structure, and I am just giving you gold silver. Remember, in CuAu3 basically it is exactly similar like that, but atomic positions will be opposite as is shown in the top figure. What is that? So, let me draw the FCC unit cells. So, what will happen is that all the face center cubic positions will be occupied by the gold and all the corner atoms will be occupied by copper. Okay. That is what is the difference between Cu3Au and Au3Cu. So, both are L12 order structures, but their the occupancy of the atoms in different positions are getting changed. Okay, so now in a BCC also same thing can happen. How? Let us talk about a BCC structure. Normal BCC structure looks like that. Okay, this is here is basically for iron and aluminium. So, in a normal BCC structure, there is a body center atom and there are 8 corner atoms. So, that means per unit cell there are 2 atoms. In an average unit cell where there is no specific site occupancy, each position can be occupied by gold or aluminum. We cannot really define which one is occupied by what type of atoms. But the moment is getting order like FeAl structure, what will happen? In FeAl structure, let me draw it again here for your understanding. FeAl structure will be like this is a compound FeAl structure, it is known as B2 order structure. So, all the corner atoms will be occupied by aluminum and central atom will be occupied by iron. specifically defined. This is iron, that 8 corner atoms are occupied by the aluminum. So, that means aluminum has 1 atom per unit cell, iron has 1 atom per unit cells, but specifically they are occupying fixed atomic positions. This can also happen in a larger scale. That is what is shown here in this case, which is basically a Fe3Al structure, Fe3Al compositions. As you see here, this is known as a DuT order structure. What is happening here is that all these if I take this unit cell, okay, this unit cell and extend in all the 3 directions, okay, as you see here, basically the way it is done is other way. I should do also the same way, otherwise it will not help you. So, let us put it in different way. Let us put the central atom as aluminum and corner atom as a iron. Okay. So, that means central atom is aluminum, corner atoms are iron, but again this is not different because the ratio is exactly 1:1. So, now if I join 8 such unit cells in all the directions x, y, z. So, what will happen? What this will be the picture. You see there are 1, 2, 3, 4, 5, 6, 7, 8 unit cells, and only central atoms are actually occupied by these unit cells, actually occupied by the aluminum atoms, and the corner atoms are occupied by the iron atoms. Remember, only 4 aluminum atoms are shown, 4 are not shown. Okay. So, in this way actually we can actually see that stoichiometry will be Fe3Al, 75% iron and 25% aluminum, and structure is known as DuT structure. It is no longer same as like the structure which is shown here, which is known as a B2 structure. So, BCC to B2 is again another order transformation which happens in a hexagonal in a BCC crystal structure. Similar thing can also happen in a this is again shown. Okay, let me tell you that in copper zinc system also such a kind of transformation happens. This order BCC structure goes to order B2 structure, and copper zinc, you see in the BCC unit cell all each and every positions is average, but in the order B2 structure corner atoms are occupied by these zinc atom and central atoms are occupied by the copper. So, that means there is a segregation of the atoms to the specific positions of the unit cell. So, again same thing can happen in hexagonal cubic close packed structure also. Normal hexagonal close packed structure will have atoms sitting at these in the hexagonal layers and also in the central atoms. Only look at these atoms which is sitting at the hexagonal layer. This is one hexagonal layer, okay, and obviously in the center of the hexagon also there is an atom, similarly here also, okay, and center also another atom, and then you have 3 atoms which are not sitting in the lattice positions, which is sitting as a B position, A, B, A, like that we know. Now, question is this is an average, okay, where we do not know that which side is occupied by what time atom, so the magnesium or cadmium, but the moment few atomic positions are fixed, then we have to talk about TO19 structure. This is an order structure, basically name is given like that. This is CPH close packed hexagonal structure, this is order structure, again similar atomic compositions, 75% magnesium, 25% cadmium. So, that means this is as a Mg3 CD. So, what will happen here is that here you see here some of the corner atoms 1, 2 here occupied by these magnesium, again here at the bottom layer, at the center out of the 3 atoms, so 1 atom is occupied by magnesium and rest are actually cadmium. So, what does it mean? Oh, sorry, these are all cadmium atoms, the black ones and white ones, actually the closed one is cadmium and open one is magnesium. So, you can see here that these ones actually there are 4 atoms, and in hexagonal cells they contribute 1/6. So, it is basically 4/6, that is 2/3, and this one is 1/3. So, 2/3 is plus 1/3 is basically 1, and then rest of is actually contributing to magnesiums. So, 1, 2, 3, 4 and 1, 2, 3, 4 by 1/6 and 4, that means 4 plus 4 is 8, 8/6, that is then it's become 4/3, and then you have a 2, 2 each, so half. So, this becomes 3 atoms. Okay, that is how actually calculation can be done. But what are the situations? What is happening is that from these to these structures there are segregations of the atoms to the specific atomic positions, and that is what is known as ordered structure. Anyway, so that's the basically definition of order disorder to order transformations. For the last 5-6 minutes or maybe more than that, approximately about 10-12 minutes, we have discussed about the definition of order structure, mainly because you may not have taught such a kind of concept previously. Now question is this: why such a kind of structure will develop? Okay, so let us go back to the gold copper. That's the basically better system to understand. Remember, in an average unit cells, it can be any type of bonds present, like gold copper, copper gold. Okay, there are copper copper gold gold. Okay, the three types of bond possible: gold copper, copper copper, gold gold. Okay, but in order structures, if you look at it, element to order structures, it's basically copper gold bonds which are preferred. If you look at here, nearest neighbors are all gold for these copper atoms. For this copper atom also gold. Okay. Similarly for these also, for the face center atoms also, now all the nearest neighbors are basically gold. So what does it mean? That means what? The bond type is which is preferred in the order structure is distinctly different from the disorder structure. So one can actually measure the bond energies between gold copper, copper copper and gold gold, and it is found that the bond energy between gold copper is basically negative. So therefore, in the free energy equation, delta G equal to delta H minus T delta S, the delta H becomes highly negative and delta Ts is basically always positive. So that means what? This term actually predominates in the free energy expression, delta G equal to delta H minus T delta S. Okay, remember, as the atom goes to specific positions, the entropy of mixing decreases. Why? Because the permutation combinations required for arranging the atoms is basically reduced. So because of that, T delta S term reduces, and that is a positive term obviously, because there is a negative sign behind it, and delta H terms increases because of the preference of the bonds between copper and gold over to gold gold copper copper bonds. That is the main reason for stabilization of these structures at lower temperatures. So thermodynamically, these order structures are preferred at lower temperature because of these bonds between these dissimilar atoms are preferred more than the similar atoms. That is the main reasons for stabilization of the order structures. That is the best way to do that. Now as you are talking about ordering, we are talking about ideal situations where all the unit cells will be looking like this. That is, all the unit cells, copper atom will go to the face center positions and gold atom will go to the corner positions. But that may not be the case always, because in real structures there will be defects. Okay, there will be defects in the sense that there will be some unit cells where gold atom may be going to the face center positions or copper atom may be going to the gold positions. How to measure that? Okay, experimentally this can be measured using X-ray diffractions, but to measure that we need to define certain things. What you need to define is order parameter. Okay, so order parameter tells you how well ordered a structure is. What is the meaning of order parameter? It is very simple. Lonely order parameter is defined as RA minus XA divided by 1 minus XA, right? That is how it is defined. So if the X-ray is the mole fraction of a element A in the alloy, okay, and RA is the number of fraction of sites which are occupied by the A type atoms. Suppose there are 100 sites, let us consider this as a gold, A as a gold atom, okay. So A is a gold atom. In CU3AU structures, gold atoms are basically sitting on the face center corner positions. So if all the face center corner positions are perfectly occupied by the gold atoms, then RA becomes 1, because that is a fraction. All the corner atoms, if you consider in a large sample, there are suppose 1 million unit cells. In all 1 million unit cells, if all the corner atoms are occupied by the gold atoms, that means RA equal to 1 for that sample. And then this becomes 1 minus XA divided by 1 minus XA, that is equal to 1. So long the order parameter becomes 1. But that is the ideal situation. This will never happen in the actual situation. Why? Because there will be thermal vibrations, there will be defects in the structures. Those are all actually allowed because of energetics perspectives. So, in that case some of these sides will be occupied by copper atoms also, some of the corner sides in the unit cells will be occupied by copper atoms. So, Ra will be less than 1. So, therefore, Ra is also a fraction, Xa is already a fraction because Xa is the mole fractions of the alloy. In case of Cu3 Xa is equal to 0.25. So, if Ra is a fraction, suppose 0.9, 90% of the sides are occupied by the gold atoms, is 0.9 minus 0.25, that becomes 0.65 divided by 1 minus 0.25 is 0.75. So, that means La become 0.65 by 0.75, that is again a fraction. So, that is actually the long order parameter. Okay. Similarly, in case of B2 structure also we can define the with same way. Okay, the definition is exactly same. So, it can be also written Rb minus Xb divided by 1 minus Xb, that is also possible. So, in the X-ray diffraction patterns, actually for the order structures you are going to get X-ray reflections, because now the atoms are actually occupying specific sites, and because atomic scattering factors are different for the gold and copper. So, there will be intensities coming of the diffraction which are not allowed by the FCC will be seen because of these differences. I cannot go in details of those, but because it is a part of X-ray diffraction, but it is possible. So, by looking at the intensity of these reflections which are coming because of the ordering, one can actually measure the lattice L, the long order parameter. But actually this is plotted like this. Now, remember, long order parameter is a function of temperature. Is basically a function of temperature. It is below Tc. Tc is the transformation temperature where disorder phase goes to order phase, like in AuCu3 is 385 degrees Celsius temperature, in AuCu is 410 degrees Celsius temperature. So, there is a temperature below which these order structures will be favored than the disorder structure, and that is known as a Tc, the transformation temperature for the ordering. Now, below that order parameter is more than 1. Above that order parameter is 0, because above that is a complete disorder structure. So, therefore, La is 0. Why? Because it become Ra become this top become 0 basically. So, because this will be same, Ra and Xa will be same value. So, therefore, it becomes 0. So, that the lattice L becomes 0. But below Tc, L is a finite value more than 0. Remember, at absolute 0 it will be 1, because why? Because absolute 0 there will be no defects presence, all the atoms will occupy the fixed positions, and then it slowly maintains that value to certain temperature, above which again after certain temperature is disordering phenomena starts happening. The more atoms will be going occupying the other sides than the specified ones, the La will slowly decrease, and then at Tc it becomes 0, correct. On the other hand, this is what is known as in case of Cu-Zn things, it happens like that way. At Cu3Au it happens exactly like this way. Order parameter maintains one value close to one value very close to Tc, and then at Tc it drops off drastically. Okay, but here in case of copper zinc, which is B2 order structure, order parameter has slowly decreased. You see, slowly it is decreasing, slowly it does not drop off 0 value at Tc. So, these two actually are different kinds of ordering. In one case, order parameter becomes 0 exactly at the Tc temperature, that means it drops from a very high value to 0 value. In other case, it slowly decreases and reaches 0 at Tc. The first one, which is shown here, the top one is known as a continuous ordering, second one is known as a discontinuous ordering. Okay. What is the difference between these two? These two can be explained very nicely by using the next plot. Order disorder transformations can be first order or second order transformations. In fact, almost all the transformations we are talking about, it can be first order or higher order or second order, many people tell. There is no third order transformation zone. So, we metallurgists tell about first order and second order transformations, and in the condensed metal physics community they tell first order and higher order transformations. So, remember, order of transformation depends on the order of the differentiation of the free energy with respect to pressure and temperature, which is continuous or not continuous. Let me explain it properly. We know that dg is basically V dp minus S dt, right. I have derived this expression, please go back. If you are not able to do, look at the books. The total differential of free energy can be written as a function of V dp minus S dt, where B is the volume, P is the pressure, S is the density, S is the entropy, and T is the temperature. Now, I can write down differential form delta G by del T is basically minus S at constant pressure, and delta G by del P at constant temperature can be written as a volume. Okay. So, these are the first order derivatives of the free energy with respect to the pressure and temperature, or temperature and pressure. Now, if in a transformations the zeroth order derivative is nothing but the function itself is continuous till the transformation temperature. Okay, that is what you see here. This is entropy is continuous, the volume is also continuous. Okay. But if the second order derivative is discontinuous, okay, then it is called first order derivative is discontinuous, I am sorry. The zeroth order derivative is continuous till the transformation temperature. You see here, this is continuous, it is not there is no jump. Okay. But first order derivative is discontinuous across the transformation temperature, then it is called a first order transformations. That means these two factors, which is del G by del T at constant pressure and del G by del P at constant temperature, must be discontinuous. How do you know that? Very simple. Del G by del T is entropy. You know, entropy can be related to minus L by Tm at the melting temperature, or at the transformation temperature, let us write Tt. Any transformation will have a latent heat, whether it is a solidification or a solid state transformations. So, at the temperature of the transformations, latent heat divided by the transformation temperature will give you the entropy change. Okay. So, that means what? If I plot this H is nothing but a latent heat here, let us write H. So, H, if I plot the transformation temperature, you see here that this is liquid, this is solid, there is a discontinuity. Okay, very clearly you can see that. Similarly, if we plot volume, okay, if we plot volume, which is V as a function of temperature, okay, you know, in a solidification event like that, volume also goes volume basically undergoes a drastic change at the melting temperature or solidification temperature. We know that volume of the solid is always lower than the volume of the liquid. Okay. So, because solid is order structure, so that density of solid is higher, so volume will be lower. A liquid is an open structure, the density of solid liquid is lower. So, that is why actually, so that means in a first order transformations these kind of situation will happen. In the second order transformations, which is basically you have to take a second order derivative of that. If I take a second order derivative of these at constant pressure, this is nothing but a del S del T, okay, which is nothing but a Cp, basically Cp, because S del S is what? Basically del Q by T, and then you can write down these as a del Q by is 1 by T Cp, basically one can write down, okay, the Cp by T dt. So, that means this is Cp actually, it is the most important factor. Similarly, if I take del G by del V square, sorry, del P square, the second order derivative at constant temperature, this will be del V minus del P, that is nothing but a compressibility, or basically related to compressibility. So, important factor is the Cp, that means Cp is important. Now, the second order transformations, both the zeroth order and the first order derivatives are continuous across the transformation temperature, but second order derivatives are discontinuous. That means Cp will be discontinuous at the transformation temperature. That is what you see here. If we plot Cp versus T, that Cp is basically showing a discontinuity here. Basically, this is a classical case of going to infinity then reaching a value, but this is like a lambda. So, that is why all the second order transformations are known as a lambda transformation, because Cp has a shape of like a lambda, it is just like these, that is why it is called. Now, upon knowing of these concepts, before I stop this lecture now, this thing can be talked in that. So, this one which is shown at the bottom at figure B is basically a first order ordering transformations, and this one is known as a second order ordering transformations, okay, because the order parameter is sharply going to 0 at the transformation temperature. Okay, there is a discontinuity, okay, you can see there is a discontinuity like this, okay, there is a discontinuity at the of the order parameter L, okay, but there is it is not, okay, the order parameter is never having a discontinuity at the transformation temperature, you can see it is slowly decreasing. So, there is no jump of the order parameter in the first case, that is why it is called a second order ordering, and this one is called first order ordering transformations. Remember, in the second order ordering transformations, latent heat is continuous across the ordering transformation. So, by simply doing experiment in DSC and others, we cannot detect such a kind of transformations. On the first order ordering transformations or any other first order transformation can be detected by using DSC, because heat evolution is discontinuous. Okay, so this is what is the basically thermodynamic definition of ordering and order disorder transformations. In the next, I am going to discuss about the microstructural features lecture of these transformations in a detailed manner.